Okay, so now we're going to turn to Rob Smith. Rob, you there?
Okay, so hello again. I'm still Rob Smith from Away Team Software, um, and this session is on implementing and testing GeoPose, which is largely based on my experience of doing this in Testbed 18. Um, Testbed 18 was about explored GeoPose for video use cases. And the way I experimented with this was to implement a 3D compass for mobile devices, which I've already spoken about. And this was originally implemented as in a web page and then ported to an app. And that was quite an interesting development process that identified several pitfalls. I thought that would be a relatively easy port, and it turned out not to be because of the way those different APIs handled orientation in particular. But avoiding these pitfalls makes implementing GeoPose pretty straightforward, I think. So let's get to it. Do you see my next slide?
Yes.
Good. So your code, presumably, you're going to implement this yourself. So your code already deals with location and orientation, or pose. So you understand how that is handled in your own software. The purpose of GeoPose is to communicate that information with others. So either we need to read data from other sources, or we need to share that data in a format that others can understand. So implementing GeoPose is easy. You'll be pleased to hear. If you want to read GeoPose, then you need to implement an import function. And if you need to write GeoPose, then you need to implement an export function. And you don't have to implement both of these if you don't want to, if you don't need to. But if you're going to do both, I would suggest you start with the export function, mainly because it's easier to implement. There's no syntax checking. Presumably, you're going to get the syntax right. So this is really just a print statement. So it's a hello world program or hello world routine, really about as simple as you can get. None of this requires restructuring of your code. That's usually the first question. Oh God, am I going to have to change everything? No, just add one or two simple functions to do the import or the export in whatever format you want. Small change means small risk, so it doesn't affect the stability of existing code. And it provides access to join our growing community of GeoPose users. So you've decided to implement GeoPose. Good choice. Where should you start? My suggestion is you start with the basics. And you've got a choice of two basic GeoPoses. You can either use angles, yaw, pitch and roll, or a quaternion for orientation. And in both cases, you use east-north up coordinates for location, WGS 84. It's not difficult to implement, as you can see on this slide, hopefully. You can see two examples on the right. So both of these are encoded in JSON, so JavaScript object notation. At the top, we've got a basic yaw, pitch, roll, which has position and angles. And underneath, we've got a basic quaternion, which has position and a quaternion. Implementing GeoPose means that you need to read or write one of these. So that's it. Told you it was easy. So thank you. It's been a great presentation. Maybe there's a little bit more to it than that. You need to implement the basics first. It's much easier to then move on to the advanced GeoPose if you need to do that. And the advanced GeoPose includes more features, things like different coordinate reference systems. GeoPose is a container, so you can put in whatever you wish. There are also more advanced features like chains, which have been mentioned a few times already. These support linked frames of reference. So the LiDAR, example of the LiDAR I talked about earlier, on a vehicle that detects nearby objects, the detections are based on the geoposes recorded in the vehicle's frame of reference. And so we can use the vehicle's geopose to relate those back to objects in world coordinates, so to identify moving and stationary objects, for example. Graphs, briefly, are branching chains. So if you have a front and a rear dash cam on a vehicle, they both share the vehicle's location, but they have different orientations. Obviously, one is facing forwards, the other is facing backwards. And then time sequences, an example of that is dashcam footage. So the camera trajectory is described by a time sequence. All fairly straightforward. But get the basics first, then the advanced stuff is much easier. So let's start by implementing those basics with position and orientation. So firstly, what is position? Hopefully there's not too many surprises here. Short answer, it's location. And for a basic GeoPose, that is an east, north, up coordinate reference system, as shown here. And we're using WGS84. So it's height above the ellipsoid. What are the pitfalls? Well, firstly, which coordinate reference system are you using? Is it WGS84? You need latitude and longitude in degrees, altitude in meters. There are other coordinate reference systems. So, for instance, the British National Grid uses eastings and northings in meters and altitude in meters. So that's not a basic GeoPose. But advanced GeoPose will handle that, no problem. It's a container. Where is altitude measured from? Is it from ground level? If you're using a drone, a quadcopter, that may be from its launch point. If you're in an aircraft, that might be above mean sea level. Or is it above the ellipsoid? If you're using GNSS, I think I'm probably preaching to the choir here. You understand the differences between these. But then which ellipsoid? WGS84 is a global ellipsoid fitted across the whole globe and can be used universally. Something like the British National Grid is fitted more closely to Great Britain. Also, are you using Cartesian or polar coordinates? East, north, up is a polar coordinate system. So you can attach a Cartesian system to these. And you can approximate over short ranges as well, but not over long distances with Cartesian. Shortest distance between 2 points is a great circle in polar coordinates. So hopefully, as I say, there weren't too many surprises there. What about orientation? So, what is orientation? It's direction. These can be in terms of angles or a quaternion. So let's look at those two separately. Yaw pitch roll. Yaw is related to left and right. Apologies if you already know this. I'm just making sure that everybody's on square one here. Yaw is left and right in horizontal direction. Pitch is up and down, above or below the horizon. Roll is related to tilt, being the right way up or upside down. And these are similar to aircraft controls if you think of it in those terms. The angles can be measured directly, so that's an advantage, and are generally intuitive. You can understand them easily. The quaternion is less intuitive, I think it's fair to say, though mathematically probably easier to deal with. It has 4 components, even though you only have 3 degrees of freedom. These 4 components are X, Y, Z, and W. X, Y, Z, the simple way to think of that is that it represents a 3D point, and that gives you a sight line from the origin, which is the direction it's pointing in. So that's an easy way to understand the quaternion. Technically, it's a versa. That just means it's a unit quaternion. It has a length of 1. And that means that the sum of squares, x squared plus y squared plus z squared plus w squared, is 1. So we can calculate w from x, y, and z. So actually it only has 3 degrees of freedom after all, despite having 4 components. There is a formula to convert between angles and quaternions. They are directly equivalent. It's just provided for convenience, and you don't have to implement both if you don't want to. So, what are the pitfalls? Firstly, the points of the compass are typically measured from clockwise from north. So north, east, south, west, in a clockwise direction. Yaw is always measured anti-clockwise from the east axis. And that might sound obvious, but it's a difficult habit to break. So yaw is 90 minus heading. And it's easy to get confused. Slip into the trap of thinking that yaw and heading are the same thing, and then suddenly nothing is making sense. I've done that myself. I said it's typically measured clockwise, but that's not always true. And that's the second pitfall, which is much less obvious. So heading may be measured anti-clockwise. So north, west, south, east. But why would you do that? It was a surprise to me, I have to say. But while you're thinking about that, let me tell you a story. I have seen a compass like that since I implemented the 3D compass. And it's in Portsmouth at the D-Day Museum, which I can thoroughly recommend if you happen to be in the area. And outside, there is a landing craft from the D-Day landings. And it's one of the big ones. It's for tanks rather than just for infantry. And you can go on board and explore. It's on the land. It's not floating in the sea. And you can climb around. So you can go up to the bridge, which is up above the main deck, which is a good spot for, gives you a good view for navigation, but it's obviously vulnerable to enemy fire. So there is a second bridge, which is down at the main deck level, it's armored, has a very poor view, but it has a periscope, and you can look up a tube with a mirror to see your surroundings. And the compass on that periscope has a heading with an anti-clockwise scale, because it's inverted, not because of the mirror, but because you're looking up, and that's the key. And that is implemented on the 3D Compass app. So you can try it for yourself. If you run the app on the phone and you turn it upside down, hold it above your head so the screen is facing down, you'll see that the compass rose flips over. So west is on the right-hand side, which seems a little counterintuitive, but have a play and you'll see. That was a surprise to me. Another pitfall I found was the angular ranges. So we have 3 angles in your pitch and roll, each with apparently a 360-degree range. But we don't need the full range to describe all possible orientations. There's some redundancy here. And the pitfall is to dismiss those duplicates and just without understanding them. Other sources may use different ranges and may make different assumptions to the ones that you make, which can lead to misinterpretation. So I can talk you through that very simply, which is to say, if you consider yaw, that's left and right, basically the heading or equivalent. So there's a 360-degree range. You can look in all directions. That makes sense. Pitch, well, you can look from straight up to straight down. So that's from plus 90 to minus 90. Well, that's only 180 degrees. If you want to look behind you, turn around. So that's a different yaw. And finally, we've got roll. So 0 is up, and you can rotate round one way to upside down, 180 or minus 180 in either direction. So that's a 360-degree range. So we've missed out 180 degrees of the pitch. So clearly that's not important. Don't dismiss it. You need to understand what that is, and I can illustrate that with an example. So also to say that this is not an issue with GeoPose, this is an issue with the yaw pitch roll angles, however you choose to use them, GeoPose or something else. So if you consider a yaw pitch roll of 90, 0, 0, so a yaw of 90, pitch and roll of 0, 90 degrees of yaw gives you north. You're looking at 0 pitch, that's towards the horizon, and 0 roll, so you're the right way up. But then if you think of a yaw pitch roll of 270, 180, 180, well, 270, that's south, right? No, it isn't. Well, it is, but you need to take into account the pitch and roll as well, because if you face south and pitch up 180 degrees, you go past straight up and you end up bent over backwards and upside down, looking behind you. So you're upside down and facing north. And with a roll of 180, that's upside down, upside down. So now you're the right way up again. So in fact, those two examples are identical, although the numbers suggest otherwise. So as I say, there is redundancy, and you do need to understand what the rest of the range does. There's also a singularity in the angles, in fact, two singularities. A pitch of 90 degrees is vertically up. And at that point, the heading is undefined, if we're talking in geospatial terms. We can choose to define it, but how we choose to define it is a choice, and others may choose differently. So that's a pitfall. Again, we're assuming that others are making the same assumptions that we make, which may not be true. At a pitch of 90 degrees, the yaw and roll axes align, and this is the cause of gimbal lock, which can cause a loss of control. For example, an aircraft pilot who goes into a vertical climb has to roll to change heading, which is not intuitive if you're not prepared for that. And obviously the consequences are bad if you get it wrong. The same singularity affects location, in fact. So generally we can move north, south, east, or west. But if you go and stand on the North Pole, which is the equivalent of vertically up, the only direction you can move is south. You can't go north because you're already there. So every direction is away from north. So every direction is south. But you may not have thought of it in those terms. So, as I say, these are pitfalls of yaw pitch roll angles rather than GeoPose. And there is always an alternative. You can use quaternions instead. But more details of this can be found in the Testbed 18 Moving Features report. And you can see the link here on the slide. So, you've implemented GeoPose. You've avoided the pitfalls. What next? Well, you need to test your software. So, the GeoPose Standards Working Group has developed a set of tools for community support, you'll be pleased to hear. And we've actually already told you about them, but I will just cover their use here for testing. These can help with testing your implementation. You've written your code, you know how it works. You are presumably going to implement a test harness. So firstly, we've got Steve Swagger's site, the solar pose that he spoke about earlier, at the address which is shown on this slide as well. That contains a number of utilities which he's covered, which can generate and validate GeoPoses. So if you've written an export function, you can test that simply by pasting your exported GeoPose JSON into the Swagger website, into one of the boxes there, and validating it by executing a post operation. Check the result exactly as Steve did earlier, and you'll see the response gives you the result to say yes or no. You can also test your import function, because you can generate a solar pose with the Swagger website, which is the GeoPose of the sun from any location on Earth at a given time. So you choose your GeoPose type, and there's the full range available there. Click on the try it out button, enter the location and time, and use the GeoPose JSON output from the get operation, which you can paste into your import function as a piece of test data to test that. Okay, so that's import and export. But there's a third way of testing, which is the 3D Compass app, and it tests the import function in a different way, because you can capture a GeoPose snapshot with your Android device, capture it to the clipboard. The location is calculated from the GNSS receiver. The orientation is calculated from the device's sensors, and you can play around with that as well by crippling it effectively in the settings to see how that affects things. You can also choose the GeoPose type in the settings. So the Compass will generate a basic yaw pitch roll, or a basic quaternion, or in fact an advanced GeoPose in a simple form. And you can paste the clipboard into a text file or an email to share it. And I've actually used this myself to gather data during a field test. It has a limited use, but it's a useful sanity check. And you can compare the results of another app that's actually running under test on the same device. And this is, which is a valuable thing to be able to do, as I say, useful sanity check. And that's available, as I said previously, to download from the Google Play Store for free at the link shown here and I shared in the chat previously. So, what have we learned? We've covered how to integrate GeoPose with existing code, pitfalls to avoid when implementing GeoPose in terms of location and orientation, where to find the tools to test your GeoPose implementation. What are the next steps? Well, that is entirely up to you. You've got the opportunity to join the growing GeoPose community, but I can only show you the door. You're the one that has to walk through it. So thank you for your time. Any questions? I saw there were some comments in the chat, but I'm only looking at my own presentation at the moment, so I can't get to that until I stop sharing.
Yeah, I was just mentioning that orientation means looking towards the orient first, so that we remember that it is east, north, up. That thing, but also that in order to apply angles, I don't know if it is in the standard or not, but the rule is to apply them in the opposite order: roll, pitch, and yaw. In that case, you are, if you apply them sequentially instead of at the same time, you avoid the issues with gimbal lock.
Okay.
Yeah.
Can you go back a slide?
I can. Is that what you're after?
It was. I thought that's what he was speaking. I have a question about this slide, but I was going to let Mikkel finish it.
Okay.
I have finished, so go ahead.
Why in God's earth is this a mix of right hand and left hand rules?
Oh, sorry. I pinched this from somewhere else. Yes, don't take any notice of the direction of the arrows. They should probably have heads on both ends. Apologies for that.
No, but it's critical that, for example, roll is a right hand rule by this diagram, right? You put your hand in the direction of the way the roll goes, you close your hand, and your thumb points in the direction of front. The other two are left hand rule axes definitions. Tell me we're not using this.
Yes, sorry. That is not accurate. It is only an indication. As I say, those arrows should probably have heads on both ends.
That would not resolve. That would make it more ambiguous.
Okay. Well, that's what it's supposed to be. I think you're reading too much into this slide.
Why are you allowing left hand rule axis definitions on rotation? Does that make sense to you? The question I'm asking, or you know,
so
what right hand rule, left hand rule is?
I understand what
good.
Right and left hand is. Yes. So yes, I'm just checking. So front is the x-axis. I mean, this is part of the problem. So looking at the web API and the Android API, they define this in different ways. And this was one of the things that tripped me up. So when you consider a device, here's a device like this, which way is up? Which way is front? Are you talking about the camera? Are you talking about the screen? Are you talking about the way you would normally hold it, like a remote control?
Yeah, I agree with you. That definition of a direction is a choice. But mixing the definition of, like shown in this figure, will screw up the dynamics. The physics of rotational motion is defined uniformly with right-hand rules. If you mix those, the calculation of any kind of circular motion, rotational motion is, I don't know what the hell you'd do.
Okay, as I say, I think you're reading too much into the diagram. I've made a mistake.
Well, no, I think you're pointing out, you said there was two different ways that existing people do this, and you're trying to satisfy both of them, and I'm suggesting don't try to satisfy, but make a choice that's consistent with universal physics definitions.
Yeah, okay. So, I mean, one of the things is that, particularly for the phone operating systems, they consider that this, hopefully you can see that, is the front. So it's basically the direction of the camera that you're looking down onto the screen, and the back of the screen is the front, but that's also the z-axis. Yes.
So so I'll just say, I believe the diagram is exactly right for aircraft thinking and terminology, and one doesn't agree. And it's
Well, go ahead, Steve. Finish your thought. I mean,
no.
I'll object after you're done.
So that's one of the confusing problems, or I don't know if it's a problem, but it's definitely a confusing aspect of dealing with rotations. There are a lot of different ways of describing rotations, and
yes.
I mean the diagram's incorrect in the point of view that you actually have to apply the rotations in order to get the right result. It's not with respect to the original fixed coordinate axes. It's actually after you've performed each of the rotations in sequence. But I think the diagram's right. But this whole thing to me illustrates that the whole terminology of of Euler angles, Tate-Bryan angles, yaw, pitch, and roll, heading, altitude, azimuth. Each one goes with a specific application domain where people believe that it's the way you should do it. And the way that it works for them interoperably, it works because they keep inside their domain. So it's I would say this is a danger warning flag.
I could believe, Steve, that you're right in the sense that somebody has done a diagram that looks like this. My experience on building control systems for satellites, control systems for automobiles, and a physics degree, and Wikipedia says this is wrong because you're inconsistent in terms of the physics that happen when the description of the laws of dynamics of physical motion. If you use this, you'll just be screwed. I'm sorry, I'm getting a little emotional. We've already done this with, lat long and long lat. Let's not do this again.
So this reflects actual practice that it boils down to the yaw part is in the wrong direction for things to work, because the yaw angle reflects measuring headings from north and going clockwise instead of measuring angles counterclockwise, which the others are. But it's baked into yaw, pitch, and roll, or pitch, roll, and yaw, as I learned it.
I've never seen that example. I'd be interested to see your example of where
Okay.
that's worked.
I think that diagram just has very little to do with yaw and pitch. That's the problem.
Well, just change it then. That's it. God.
If I, in my innocence, could summarize the discussion that's just happened, I appreciate, George, you bringing this up. I want to say, I think this illustrates if the community of all the implementations of location and orientation could agree on one system, there'd be a lot less confusion and a lot more interoperability. And so the specification is clear on how these are defined, and how to use them requires to paying attention to these different what Rob called pitfalls. But I think one of the approaches of getting around this is to have code snippets that are implemented in a manner that's consistent with the specification, and that people can then use the same basic components when they're implementing. This is a session about implementation. Again, I could be completely wrong, but I think that's where the direction we're going in. Rob, did you want to say anything?
Yes, I don't disagree that there are mistakes in this diagram. That's not really what it's trying to show. It's really just labeling the axes and the name of the rotation around the axis. So you've associated front with roll and pitch with left and right axis, and so forth. I think you're reading too much into it. No, but as Christine says, there is inconsistency with the way these are defined in various communities, and they tend to stick to their own communities. We are trying to share. We are trying to break down those silos. So we are running into those obstacles, and you will run into them pretty quickly too.
Yeah,
Rob. Yeah, so Matthew Percy again.
Hi.
Just to chime in on this, just observing with a bit of shock the amount of community silos that are being created by different applications we can argue whether they're right or wrong, but different communities applying physical principles in different ways and talking about the same terminology with different semantics is you're up or you're down or exactly. And this, to me, it just strikes a major problem for interoperability. If you're trying to use the same language to bridge those silos, because each of those communities are welded in many cases to their particular use case application of those terms. I actually see a real opportunity here for something like discrete global grid systems to come in and provide an alternate way to describe location and direction in a community agnostic way that can then hopefully help us bridge some of these challenges, let alone the mathematical backflips that you've had to do just in implementing the 3D compass on different platforms.
Yes, and that was a complete surprise to me. That I thought, well, I've got it working, so doing a port should be pretty straightforward. And then spent several weeks going, why doesn't this work? And ultimately had to pull the code apart to say, what on earth is going on here? Why is it not working? Oh, hang on. The numbers I'm getting don't even match up with the documentation. So let's just start from scratch and do it empirically, which is how I ended up doing it.
Yeah. Can I just share the illustrations?
Yes, please. Go ahead, Mikhail.
I created to try to solve this issue, like having this illustration to include all the different visualizations of orientation, position, and talking about local X being east, local Y being north. But I have realized that the illustrations I created back in the day to represent orientations, like in this case, the orientation of GeoPitch roll, need to be updated to include the right rotation, like the direction of the different angles here, so that we can represent the different rotations, whether it is a lookout system like I have here, or other kinds of rotations, like the ones mentioned in the chat about rotors. So while right now, just clarifying what is aircraft principal axis or angles and quaternion is complicated enough, I am going to look into it and create better illustrations so that I can share it with you, Rob, and not repeat the same mistake in the illustration in the slide. Okay?
Yeah, sure. And thanks to George for pointing this out. I mean, this is the sort of feedback we need to say if we are making mistakes, if we are putting the point across.
Confusing.
Yes, avoid confusion.
Yeah, and I will create the illustrations to avoid that.
Yeah, it's Chris Little. I just want to back up George because I've got a maths degree and I did all the angles and it's confusing. And let's stick with Wikipedia and make sure we're consistent. And I think we need to just document it and just to say, well, these issues occur all the time, right? Are you looking at the sky or are you looking at the ground when you're measuring your orientation? You get, one's left-handed, one's right-handed. Are you looking at the screen or is the screen looking at you? And that's the difference between the left-handed and right-handed. And so they happen all the time, and you don't know what the context of the person who wrote the software was, right? So I think we just have to be very explicit and have some good documentation, very simple to understand, and that's it. And I'm sure Steve and Michael have got it right.
So I actually consider myself to be viewpoint free in this discussion, but I guess my viewpoint maybe is something that people could disagree with, which is there are these communities which use representations or conventions which are idiosyncratic, let's say. And so my direction in dealing with this has been to try to learn and identify these different weird domains, document what's going on there, and then if they have a stupid way or a way that's not the way I would have done it to do 3D rotations, let them, as long as we can document it and provide a structure that corresponds to their usage. So rather than saying we have a universal, so we could just say use quaternions. They'll work for anybody. That we actually do the work of understanding what's going on in these different communities, and we bring those in 2 or 3 at a time into the standard and say, if you are working in a horizontal plane and you think altitude and azimuth is what you need, then use this. But I think that's my point, and I think we've run out of time because the.
I want to say I agree with you, Steve, in the sense of you need to address all those communities, but I think you need to make a strong choice about which is the normative one you're going to use. And for the love of God, make them all right-hand rule angles.
Well, I mean, that argues for using something like quaternion that doesn't have any pitfalls, and pretty much everything else does. So,
I don't think you can get away from yaw, pitch, and roll.
yeah.
I think
so,
you have to define yaw, pitch, and roll.
Yeah, but it's defined by the people that use it, even though it's.
You have crazy,
Yeah.
traditions like that, just.
Put them in an annex, say,
Yeah.
I think that's a contribution of the standard, that it actually figures out what's going on, and maybe it is only informative, but it's in there. Yeah.